In this video, we're going to talk about some applications of Euler's formula. So recall Euler's formula. What it says is that e to the ix equals cosine x plus I sine x. Okay, so I'm going to highlight this. This is Euler's formula right here. Okay, so I want to talk about a couple consequences of it. So the first is there's something nice that we get if we plug in x equals pi. Plugging in x equals pi into this, we will end up with e to the I pi equals cosine of pi plus I times sine of pi. And simplifying, we get e to the I pi equals cosine of pi is -1, sine of pi is 0, so we get 0 here. And if I rearrange the terms to move the -1 to the left side, we get e to the I pi plus 1 equals 0. And this equation here is referred to as Euler's identity. And one of the reasons why it has a special name is because this equation involves 5 of the most important numbers in math. It has 1, it has 0, it has pi, it has e, and I all combined into this one simple looking equation. Okay, so let me talk about another consequence of Euler's formula. And this one's going to be the one that's more useful to us in terms of what we can do with it. So it's possible to use Euler's formula to get formulas for sine and cosine that involve I. So let's see what that looks like. So this is Euler's formula here. I've just copied it down. And then what I'm going to do with this is I'm going to replace x with -x. So I'll get I to the -x, and I'm going to go ahead and substitute a -x to the right-hand side. Cosine of -x plus I times sine of -x. Euler's formula is true for any value of x, so no matter what I plug in for the x, it should be true. And I'm just plugging in -x for the x. Okay, so now I'm going to use the even or the oddness of cosine and sine. Cosine is even, which means cosine of -x equals cosine x, because this is an even function. And on the other hand, sine is an odd function, so sine of -x would be negative sine x. That's because sine is an odd function. Okay, so what that's going to let me do is it's going to let me rewrite that second equation a little bit. So let me just copy down the first one. E to the ix equals cosine x plus I sine x. The second one, I'm going to simplify it. We get e to the -ix on the left. On the right, we get cosine x minus I sine x. Okay, so I'm going to label these two equations that we have here. So there's one on the top. I'm going to call this equation 1, Euler's formula. The one on the bottom, I'll call this equation 2. And now let's add them. So if I add 1 to 2, on the left-hand side we get e to the ix plus e to the -ix. And on the right-hand side, the I terms cancel because one's positive and one's negative. And we will end up with 2 cosine x. And now I can isolate for the cosine x by dividing by 2. So we get cosine x equals e to the ix plus e to the -ix over 2. Okay, so this is an equation for cosine. Cosine equals this fraction that has e's and i's in it. And it looks a little bit weird, but still, it's interesting nonetheless. So let's see if we can do something similar to get sine isolated. So instead of adding them, how about we subtract these equations? Let's do first equation minus the second equation. And if we do that, we get e to the ix minus e to the negative ix on the left. On the right, the cosines will cancel, and we'll get 2I sine x. And now I can isolate for sine by dividing by 2I. So sine x equals e to the ix minus e to the negative ix over 2I. And that's a formula for sine x. Okay, so one thing that we might notice about these formulas is that, so the one for cosine, we might notice that this looks similar to the formula for hyperbolic cosine that we've talked about before, cosh x, which is e to the x plus e to the negative x over 2. It looks pretty much identical to that, except the e is gone. Sorry, the I is gone. And we can say the same type of thing about sine x. This is similar to the formula for sinh, for hyperbolic sine, which is e to the x minus e to the negative x over 2. So same idea, it's that, but just with an I gone. So this is actually one of the reasons why hyperbolic sine and hyperbolic cosine are defined in the way that they are. So hopefully these definitions seem less arbitrary now. Because initially when we talked about hyperbolic sine and hyperbolic cosine and they had these e's in them, it might not have been clear why this thing that has e's in it is called like sine or cosine. And again, like I mentioned, the key reason is of this similarity to this complex way, the complex form for cosine and the complex form for sine. Okay, so one of the main uses of having these complex number formulas for sine and cosine is we can use them to more easily obtain trig identities. So I want to show you how useful this can be with an example. Alright, so I want to begin by noting something. I want to use an exponent property. So if I have e to the ix times e to the iy, when I multiply these, I add the exponents. So I'd get e to the, factoring out the I parentheses x plus y, I'd get this. And now let's apply Euler's formula to both sides. So on the left-hand side, e to the ix would be cosine x plus I sine x. So that's e to the ix. E to the iy would be cosine of y plus I sine of y. And then this equals what we have on the right. That would be, using Euler's, we'd get cosine of x plus y plus I times sine of x plus y. Alright, so now let's distribute out the left-hand side. So if I multiply the cosine x times the cosine y first, we would get cosine x cosine y. And that has no imaginary part to it. That's just a real number. There's another pair that I can multiply by to not have any i's, and that's when I multiply the I sine x times the I sine y. Multiplying those will give me minus sine x sine y. So that is completely real. There are no i's in there. When we multiply the other pair, so cosine x times I sine y, and when we also do I sine x times cosine y, we get things with i's in them. So doing that, we'd get plus I, and let's just factor out the I, times sine x cosine y plus sine y cosine x. Okay, and on the right-hand side, we get the same thing, cosine of x plus y plus I times sine of x plus y. So now this brings me to our key observation. So we have complex numbers on both sides because we have the I. So the observation is if you have one complex number, something of the form a plus ib, and that equals another complex number, c plus id, this is true assuming that the A, the B, the C, and the D are completely real, this is true if and only if the A equals C and the B equals D. In other words, what I'm saying is the real part here and the real part here, they have to be the same. And the imaginary part here and the imaginary part there, they have to be the same as well. Okay, so if we do that same thing to the equation that we just have, what's the real part on the left? Well, the real part is this whole thing. That doesn't have any i's in it. That's going to be equal to the real part on the right. So let's just write down an equation where those are equal to each other. We get cosine of x plus y equals cosine x times cosine y minus sine x times sine y. And that is a trig identity that you may or may not remember. I know it's probably been a while, but this is a trig identity. Okay, so we can get another trig identity really quickly by equating the imaginary part. So the coefficient of I here, so this whole thing, this coefficient of I, equals the coefficient of I on the right-hand side. So that gives us equation number 2, which is that sine of x plus y equals sine x times cosine y plus sine y times cosine x. So again, equation 1 we got from the real parts. I'll color that in yellow. Equation 2 we got from the imaginary part, so I've been coloring that in green. Okay, so notice how quickly we were able to get these trig identities by using Euler's formula. That's one of the reasons why it's so useful. And now that we have these, we can actually quickly get some other trig identities. So we can quickly get others by some substitution. So I'll just show you one example of a type of substitution I could do to get some more trig identities super quickly. So for example, what if we just substituted and let y equal x? If we do that, the first equation becomes cosine of 2x on the left. On the right-hand side, we would get cosine squared x, because we get cosine x times cosine x, that's cosine squared, and then minus sine squared x, and that is a trig identity. In the second equation, what does that become? Well, we're going to get a formula for sine of 2x. Sine of 2x would be equal to, so we'd get, what would we get here? Sine x cosine x first, plus sine x cosine x. So we're adding the same thing to itself. That's 2 sine x cosine x. So we quickly got these two other trig identities very quickly from 1 and 2 here. So it is possible, if I want to get just these directly, it is possible to get these two that I just got here directly rather than having to go through equations 1 and 2. So let me just make a note of that. We could also get these directly from the sine and cosine formulas. So for example, for the cosine x and the cosine squared here, if you were to plug in what cosine is, like it's e to the ix plus e to the negative ix over 2. So doing that type of thing, and then showing that the left-hand side and the right-hand side are going to be equal. It's possible to do that just to get it more directly. And we're going to see this on the homework. Alright, so in terms of our goals, I've actually jumped around here a little bit. We have talked about goal 3, applying Euler's formula to quickly derive trig identities. So I'll end this section with a video, shorter video, on using Taylor's series to evaluate limits.